Hello everyone, welcome back, and in this video we'll be talking about the nested logic operations, and we will explain the nesting stack and where it lies in the memory map of the PLC. But first, let us look at this example to see why nested logic is needed in our program. So if we look at this example, and let's first look at this AND operation. For this AND operation to be executed and for us to know the result of that AND operation, we need to know the values that are present here. But each of those values aren't provided by an input or aren't stored directly in an address. Instead, in our case, these values need to be calculated using another AND operation. So you can think of there being an operation here that needs to be executed and the result then needs to be executed here. And for that, we have our nesting logical instructions. These nesting logical instructions, like the AND with nesting opened and the OR with nesting opened. Each of them has a first symbol used for previous basic logic instructions, but with an open bracket after it. They do not take an address after them. Instead, the instructions do come after them. The instructions that need to be executed need to come inside them. So basically, and after these instructions, we have to provide a nesting closed instruction. So let's first construct our example code. We want to implement this functionality. Let's say that this is M3.0, this is M3.1, this is M3.2, 3.3, 3.4, and 3.5. So let's begin. And we will start with our basic example. Remember, when we do the ANDing of two addresses, we needed an AND operation for each of these inputs. So basically, if we wanted to implement that AND operation, if we wanted to implement that AND operation, we would need two AND instructions, two basic AND instructions in our code. But for that instruction, these two branches are not provided directly by means of an address. So how do we actually write that in our code? We will first remove this address here, add a bracket here, and then close the bracket. The same goes for the second input of the AND of the second of the AND operation. So this is how we actually implement that part. Inside the part, we have to provide our two inputs. So let's start with the second input. The second input contains the ANDing of two inputs. And as we said, they will be 3.4 and 3.5. We have to first add M3.4 and another basic AND instruction of M3.5. And now we have completely implemented this part. So this part gets executed and the result of that part is used for that AND operation. So basically for that AND operation, we needed to add these two nesting AND brackets. And for the instructions that is inside, the instructions that are inside the first block, we needed to add those instructions to compensate for this part. Now let's move to this part. In this part, we have another AND operation. So let's start adding it. One input one by one. So basically, we first have and M3.0 for the first branch and M3.1 for the second branch. And what we need to do with the with the third branch, basically, if we look at the third branch here, it is not provided directly, so we will use a bracket, open it here, so another bracket has to be used. And inside the bracket, we need to put our instructions. So inside the bracket, we will implement this basic AND operation. And so we have a M3.2 and another AND operation for M3.3. And this is how nesting is implemented and how our example will look. So this is, so we use nesting when the input to a logical instruction is not provided directly. Instead, it is provided by another logical instruction that is executed inside one of the inputs of that logical instruction. So for this branch, we needed to execute this instruction, this AND instruction inside the branch, and you can keep adding levels or nesting levels according to your need. Of course, your need is determined by the nature of your logic. So you start with a diagram like this, and you then turn it to the nested logic we wrote in our example. Now, this logic actually cannot be executed only with the help of the status word register of the PLC. Instead, it needs to use the nesting stack to implement the nesting functionality. So let's first look at the nesting stack. So the nesting stack actually looks like this. First it has 3 columns, or it stores 3 entries for each instance or each call of a block with nesting. So when this block is called, it will actually store an entry in that nesting stack. We will talk about that in a little while. But basically, what it does store, it just stores the previous value of the RLO and the previous value of the orbit together with the function code. So if it was an AND function, it stores the code for an AND function. If it was an OR function, it does store the code for an OR function, and so on. And when the nesting closed instruction comes, it should use that entry and combine it with the result of the logic that was executed inside the brackets. So that's an overview of how the nesting stack works. But first, we need to know where the nesting stack lies in the memory map of the PLC. The nesting stack exists in the same place where the block stack is used. The block stack is another stack we will talk about later that is used for block calls, to handle block calls and nesting of blocks. But for now, for nesting of logical blocks, we are talking about the nesting stack, and it lies in the system memory of the PLC. Now that we have known how it actually looks like and where it lies in the memory map of the PLC, we will see how a nested logic operation gets executed step by step. But first, we will need to start debug mode on Simatic Manager. And now let's first see where to view the nesting stack in the PLC sim, we will just have to go to the view menu and select stacks. And here the nesting stack is viewed. But as you can see here, although the program is running, you cannot see anything in the nesting stack. The reason for that is that the nesting stack can only be viewed in debug mode, as when an instruction gets executed, as when an instruction like this gets executed, it pushes an entry into the nesting stack, but when this instruction comes, it just erases that entry as it is already processed. So the nesting stack will not be viewed here. Remember, the program itself will all run in a scan cycle of about 50 milliseconds. So you cannot monitor the nestings, and you cannot monitor the nesting stack like we do with the status word register after each block. So in order to do that, we basically need to first go to debug mode of the PLC. And for that, we need to go to the online block that is stored on the PLC. So let's first close monitor mode. In order to move to the online block that is stored on the PLC, we can actually do this two ways. First, we can use this point to go directly to the partner block of this block that is stored on the PLC. So if you can see here, it says open offline online partner. So you use this button to toggle between offline and online block. If we press it, it tells you, do you want to change your current view? We say yes. And this is our online block. You see here, it is highlighted in the title bar, and the word online appears here. So this is the first way to open the online block that is downloaded on the PLC. We have another way of opening it. So let's first close it. The second way is going back to Simatic Manager and using this button that says online. So by using it, online view is actually displayed. And in online view, you will see all the blocks that are already downloaded on our PLC, including these system functions and these system function blocks, and the user code we downloaded, which existed in OP1. So from here, if we double tap it, we can open the online block that is stored on the PLC. Now that we have opened the online block that is stored on the PLC, let's see how we can start debug mode. So basically, if you come here, you will see a debug menu. In that debug menu, you need to first go to operation and change the current operation from process operation to test operation. But for you to be able to do that, you need to put your PLC first to run B mode. In this mode only, you can run test operation or debug mode of the PLC. And let's press OK. So now let's first assume the state of our inputs to be like this. We have the first two addresses having zeros, so these two addresses contain zeros. This third address is 0, and the fourth address is 1. And let's see how this part actually gets processed. After we have started our debug mode, we will just place our first breakpoint at the start of our code. And what we then need to do is that we need to activate that breakpoint. And after activating that breakpoint, we will see this arrow indicating that program execution was halted here before execution of this instruction and after execution of the previous instruction. And a screen will be displayed displaying the content of the status word register and other things we will come back to later. But what we are concerned with now are the values of the status word register. And in debug mode now, you can see the values of the status word register and also what actually happens inside the nesting stack. So let's start by executing the first instruction. And by that, what we need to do is to come to this icon, which proceeds to next statement. But before we execute it, let's say what it will actually do. First, this nesting instruction will come. It's a nesting and instruction. It will come and see that the first check bit before it was 0. So it is the first instruction. So instead of pushing the previous value of the RLO, which was 0, into the nesting stack, what it will actually do is that it will push 1 into the RLO entry of the nesting stack. So let's start by doing that. Let's execute this nesting and statement by going here. And now that this instruction has been executed, as you can see here, first, let's have a look at the status bit after execution of that instruction. Remember that instruction had no address passed to it, so what it will reflect is a status of 1 always in the status bit after execution of that instruction. And now let's have a look at the nesting stack. So what happened? This end instruction came, found that the first check bit before it was 0, so it decided to push 1 to the RLO and the push 0 to the OR bit. So what it actually does when the first check bit before it is 0, it will push 1 to the RLO and 0 to the OR bit. If it was 1, if it was previously 1, then it will push whatever the current values were, as we will see with the next nesting and instruction. But let's take it step by step. So now we have 1 pushed into the RLO inside the nesting stack and 0 pushed to the OR bit, and the function code for an AND instruction is pushed. So this occupies the first entry of the nesting stack. Now let's move to the second instruction. And the second instruction is a basic AND instruction. So when this instruction comes, it will see that the first check bit before it was 0, so it doesn't need logic from the previous instruction. What it will do, it will just copy the content of M0.3 to the RLO, but M3.0 to the RLO, but M3.0 has 1 stored inside of it. So after execution of that instruction, we will see that the arrow came here, and what will happen is that the value that was stored in that address will be reflected first by the status bit. This value is actually pushed to the RLO because it saw that it was the first instruction, and then it will actually set the first check bit to 1, as we previously discussed with the operation of the basic AND instruction. The second AND instruction will also behave according to what we discussed previously. It will come, see that the first check bit was 1, look at the current value of the address. As it is 1, it will be combined with the previous value of the RLO, which is 1. So let's execute the second basic AND instruction and see what happens. So as you can see, nothing changes. And we still have our nesting entry placed here. But in our example, we had inside this nesting, we had another nesting taking place representing this branch. So let's see what actually happens. Our PLC came to this instruction. This instruction comes, and before it gets executed, it will see that the first check bit was already 1. So seeing that the first check bit was 1, what it will actually do is that it will store the current values of the RLO and the OR bit in another entry inside the nesting stack. So after this instruction gets executed, let's execute that instruction. And as you can see here, a new entry will appear here in the nesting stack, indicating that the value of the RLO was 1, the value of the OR bit was 0, and the instruction or the function code was of nesting and type. Now we come to the next instruction, which will be executed similarly to what we discussed, as if it was a first instruction. And because the content of this address is 0, we expected to change the first check bit back to 1, put 0 inside the RLO, and reflect 0 in the status bit. And that's what we will see now. Let's move to the next instruction. And as you can see here, this is the result. We expected to change this to 1 again. Okay, now we come to this instruction. After this instruction gets executed, what we expect is that logic from the previous instruction should be combined because the first check bit was 1, and so because the content of this address is actually 1, we know that we have 0 combined with an AND instruction with 1 will yield 0 stored in the RLO. So we expect to see here 1, 0, and 1 reflected by the status bit, which is the current content of this address. And let's go and execute that instruction. So let's move here. And this is what we actually see here. First check bit still at 1, RLO, change it to 0, and status bit change it to 1 as the content of this address is 1. Now we come at the first nesting bracket. And the first nesting bracket or nesting closed instruction you will face will close the most recent nesting instruction. So we will start with the second entry inside the nesting stack. And what it will actually do is that it will take the previous values of the RLO and the OR bit. And for simplicity now, we assume that OR fulfillment is not achieved as it is not used in this example. But if it was achieved, it would take it into consideration the same way as we previously discussed the AND instruction. So now let's see what will happen. The second entry had its RLO actually equal to 1. So the value here, the value of RLO here is known previously to be 1 by the entry that was stored here, and this value will be combined with the result of this entire nested block. So the result of this entire nested block was here before the bracket stored in the RLO was 0. So 0 from here will be combined with 1 from here by means of an AND operation that is seen here. And what we expect is that 1 combined with an AND operation with 0 should yield 0 in the value of the RLO. So now let's execute that instruction. And as you can see here, an entry has been removed from the nesting stack and the RLO was set to 0. And as this instruction doesn't have an address passed to it, after its execution, it will display 1 in the status bit. Now we have closed the first nesting and we have actually done this part. Now we need to close this part to close the value inside the branch. So basically, if we move back, we still have our first nesting that we started up there. We haven't closed it yet. And remember, when it found that it was the first instruction, it did push a value of 1 inside the RLO. So now this value of 1 will actually be combined with the result of the logic that was executed inside that block. And basically the RLO here was 0, so we will have 0 combined with 1 yielding 0 after execution of that instruction. So let's summarize what we actually had here. The first nesting instruction comes, and as you can see, after execution of this instruction, you will see that the last nesting entry that was added to the nesting stack was removed. The new value of the RLO has been updated here, and now we can finally move to the final part of our example. And in that final part, we had one nesting block that had these two entries inside it. We assume that both of them were 0, so when we come here, this instruction will find that the first check bit before it was actually 1. So the first check bit before it was actually 1. So previous logic is actually useful to this instruction. So it will store the previous value of the RLO, which was already 0, into the nesting stack after execution, and set the first check bit and the OR bit back to 0 for the logic inside to be executed separately. Now we move our marker here. So we are before this instruction. This instruction has been executed, an entry has been started in the nesting stack having 0 stored in the RLO and the OR bit, and a function code of AND stored here. Now these two blocks will get executed the same way as we discussed previously. So let's skip them. And actually, because both of them are zeros, the result of logic operation after execution of that instruction will also be 0. So now this instruction comes, and when it comes, it will check the previous it will actually close that nesting we started here. So what it will actually do is that it will combine the value of the RLO that was previously here before execution of that instruction with the value that was yielded after execution of this second instruction. So RLO from here will be combined with RLO from here with an AND instruction, and because both of them are zeros, we expect the result of logic operation after execution of this instruction to be 0. And now, as you can see here, the entry was removed from our nesting stack. And then we come to our assignment instruction. Our assignment instruction, as we discussed previously, it will just push the first check bit and the OR bit back to 0, transfer the current value of the RLO to the current address, which M3.7, and reflect that value to the status. So we expect all of these actually to be zeros after execution of that instruction. And as you can see here, after moving from that instruction, we can see that all of these are zeros. Now, let's say we are done with our breakpoint and we want to actually go back to normal operation. What you need to do is first to come to the debug menu and disable the breakpoints by unselecting this. After disabling the breakpoint, note that the program execution is still halted somewhere. So in order to stop this halt, we need to go back to the menu and click resume. And now the program is running normally back again. We just need to come first and change our mode from this operation tab back to process operation. And you can actually now go back to your offline block. Yeah, but first, it's actually required that you remove your breakpoint. So to remove this breakpoint, you come here and you click delete all breakpoints, and you go back. You can now go back to your offline block. Now in our offline block, you can see if we did monitor mode, you could actually see the value of the result of logic operation after execution of each instruction, even nesting instruction. But without going into debug mode, you wouldn't know how this result was reached or how we arrived at it. Now let's summarize what we said about nesting logic operations. So let's go back to our presentation. Basically, each nesting logic operation represents the instructions that a branch contains. So if we look at this branch for this AND operation, it contains these instructions. So that's our first nesting that was discussed. The second nesting that came is that within the first nesting, we had these branches, the first branch, the second branch, and the third branch, but the third branch was provided via instructions. So for the third branch, we had another nesting inside of the first nesting. And here also the second input for the AND operation had instructions inside of it. So we needed to also use another nesting here. So a total of 3 nestings were used to implement our examples. Now, nesting instructions, whether they are AND or, they actually do behave quite similarly. If the nesting instruction came and found that the first check bit before it was 0, what it will actually do for an AND nesting is that it will push 1 into the RLO and 0 into the orbit. And if it found that the first check bit was 1, then it would push whatever the current value of the RLO and the orbit was into the nesting stack. If we were dealing with an OR operation, when it comes, it will first find that the first check bit before it was 0. So it actually needs the result inside the OR, or inside the brackets to be equal to the total result, and for that it will actually have to push 0 into the RLO and 0 to the OR block. So a nesting AND will push 1. A nesting AND, if it comes and finds the first check bit was 0, will always push 1 to the RLO and 0 to the orbit. Nesting OR, if it comes, there will be a slight difference and it will push 0 to the RLO and 0 to the orbit. Whether it be this instruction or this instruction, both of them will reflect 1 in the status bit after their execution and set the first check bit and the orbit back to 0 for the logic inside to get executed separately. And then at the end of your nesting block, you come at the nesting closed instruction. And the nesting closed instruction, what it actually does is that it actually will always reflect a status of 1. It will process the entry that was placed by the nesting opened instruction based on the function code that appears inside the nesting stack. So if it was an AND nesting, the RLO or the latest RLO from before the bracket comes will get combined with the content of the nesting stack with an AND operation. If the function code was OR, then it will be an OR operation. And this is how the nesting close operator actually calculates the new values of the RLO and the OR status bit. Now in this video, we have explained nested logic operations, how they actually work, what is the nesting stack, how it is populated, and how it is evacuated after that. And nested logic operations will enable you to construct complicated logic. In fact, any complicated logic that you want to implement, you can implement using nested logic blocks. Now, in our discussion, we used an example that had primarily and blocks with nesting opened and nesting closed operation. And this example didn't involve use or change of the OR status bit. So in order to explain how the OR status bit actually changes during operation of a nested code, we will just need to take another example, and that example will come to the next video. So stay tuned. Please like and sub the channel.